Good morning, pre-calculus. We're in log land, and we are learning about the log rules and log laws and how to solve logarithms, and we saw where logarithms come from at the beginning a little bit. Anytime that there's a wide range of values, and sound is a good one. We talk about decibels, the intensity of sound. Something as quiet as a whisper all the way up to a jet engine taking off. There's such a wide range of values between there that by putting it on a logarithmic scale, we help shrink those down. So the differences between those are big. The pH scale, if those of you are in chemistry, and acids and alkalines and bases, that's on a logarithmic scale. Earthquakes are measured on a logarithmic scale as well. I'm trying to remember the Richter scale that I was trying to get at, but we're solving all these things, we're getting these different rules, and we're being able to solve equations. That's where we're headed. So there's one problem I just wanted to show you, and I remember being in your seats in, I guess it was my junior year of high school, thinking, I'm good at algebra. I can solve all sorts of problems. And then I remember my pre-calculus teacher putting this particular problem on the board, and I was stumped. And that's going to lead us to where we're going. So let's take a look at it. The actual problem isn't difficult, but it was new. There it is. 3 to the x equals 15. And I remember thinking, well, sun's coming in. I remember thinking I can square root it, but that's not going to do me anything. I can't divide by 3. I was stuck. We were at a point in my math life that I can't solve this. So I needed a different tool. And a logarithm is that tool. So something we are allowed to do, just like you can add 2 to both sides of an equation, just like you can square root both sides of an equation, we can take a logarithm of both sides of an equation and have it still remain true. Still, we're not messing with the equation itself. We're not changing it. So that's what I'm going to do. I have 3 to the x equals 15. I'm going to take the log base 10. So I'm just going to call it the common log. I'm going to take the log of both sides. See if I can move this over out of the sun like a vampire. Sure. Now, where I couldn't reach the x, where I couldn't solve for the x, now I can, because if I have an exponent inside of a logarithm, we learn the exponent rule, I can multiply that out front of the logarithm, and now it's out here where I can solve for it. I can now get x by itself. I can divide, now that this says times log of 3, I can divide the log of 3 to the other side, and I can jam this in my calculator. I can just do log of 15, log base 10 of 15, divided by log base 10 of 3, and I will get some decimal. 3 to what power equals 15? It's going to be an irrational number, but now we have a really close approximation with my calculator. It's about 2.46. Okay, so that's how we solve those types of problems, exponentials. We can take the log of both sides, but this is actually going to give way to a kind of neat property for us. So here it is. I said, hold up. If I go through and I solve this problem by taking the log of both sides, we got this as an answer. Well, the very first thing we learned in this class was how to translate exponentials to logarithms, and I would get this. So kind of like our derivations we've been doing so far in this section, if this thing is equal to x and this thing is equal to x, that must mean these two things are both the same. They're equal, and they are. Log base 3 of 15 is exactly the same as log base 10 of 15 over log base 10 of 3. And we get something called the change of base theorem. We can write any logarithm we want with any base we want. We like to use base 10 because that's what our calculator does. Or we could use the natural log. It wouldn't matter. Same exact problem here. 3 to the x equals 15. I took log base 10, but I could take any base I want. I could do log base 7. I don't know why I would. I would take the log base 7 of both sides equals log base 7 of 15. Okay. I could still bring the x outside with multiplication and then divide over log base 7 of 3. So notice we have log base 7 of 15 over log base 7 of 3. If I had written this in logarithmic form, it would be log base 3 of 15 equals x. Can't see it. So these are the same. I can choose any base I want. I chose 7. We like to use 10 or ln, base e, the natural log, because that's what our calculators do. But we can change and write these using any base we want. It's called the change of base theorem. Okay. Here it is, written out all fancy. One thing I like to mention when we do this, if I'm looking at log base A of f, log base A of f, f is on top of the a. If we look at it like spatially, f is over the a. And when I do the change of base theorem, any base I want, but the f is still on top of the a. And that'll help me remember which one goes on top. Log base n of f, log base n of a. We can choose any base we want. So here's a typical problem. It says use the change of base theorem to evaluate log base 7 of 3. Now I get some of your calculators can actually do any base you want. It wasn't always the case like that, so I want us to use the change of base theorem to make this happen. Now I'm an old fuddy-duddy, and I can't remember exactly what this acronym stood for, but I think I have it down to show me what you would type on a non-cheating calculator, a nice clean calculator, I don't know, a calculator that doesn't just do log base 7 of 3. So what I'm getting at is use the change of base theorem. We can rewrite log base 7 of 3 as the log of 3 over the log of 7, log base 10, log base 10. I can jam that in my calculator. It gives me about equal to 0.5646. Okay? Change of base theorem. We have this thing locked down. I'm going to show you one last thing. We're going to solve this equation together. I'm going to do it 2 different ways, and I'll let you decide which way do you think is more appealing. Which way would you attack it? So here is the first one. Here's the actual equation. 1 plus 2 to the, see if I can block this one, 3x minus 1 power equals 117. Okay? We'll attack it 2 different ways. Both ways are going to start with the same thing. I'm going to subtract that 1 to the other side. And it looks like this. Next, I'm going to take the log of both sides, just like we did on this example a second ago. Okay, so I took the log of that side, log of that side. Next, I have an exponent in my logarithm. I can bring that out front with multiplication. So there it is. I brought the exponent out front with multiplication. And now we're trying to get x by itself. Solve the equation means get x by itself. So this says times the log of 2. I'll divide that over to the other side. Excellent. Now I'll add 1. Excellent. And finally, I'll divide by 3. I'll jam that all in my calculator and get about equal to 2.62. And that's what we were going for. Okay. Now let's look at it doing this problem a different way. Probably using the change of base theorem if I'm not mistaken. Okay. So the first step is still the same. I move the 1. Remember there's a 1. I move the 1 over and I got this. From here, we can go to scale 1. It's an exponential. I'm going to write it as a logarithm. So it's going to be log base 2 of 116 equals 3x minus 1. Awesome. From here, with my calculator, I think I'm probably going to add 1 just like we did. I'm going to add 1, and I'm going to divide by 3. Yeah, that is what I did. Add 1, divide by 3. And now log base 2 of 116, using the change of base theorem, I could just call that the log of 116 over the log of 2. That's what we just learned. So there it is, log of 116 over the log of 2. And if you notice, they're the same thing. We'll get the same answer, obviously it's the same question. So it's kind of up to you. Which one was more appealing to you? Was it to take the log of both sides first and then solve? Or was it to write an exponential as a logarithm and eventually use the change of base theorem so I could jam it in my calculator? All up to you. But we're solving logs. I would throw this change of base theorem at you. Something I've seen on the ACT or SAT maybe once or twice. It's not the most important thing, but it's on there, so now you've seen it. I'll give you a couple of problems on your stamp to practice with it. Alrighty, moving on.